All right, Alg2 3.5, first day, only day of 3.5, but it's a little tricky. So we're just going to go problem by problem kind of on the Savas examples. So I would recommend you watch an example of, like, let's say problem number one, and then go to Savas and try it on your own problem. So it's a little structured for you. So here on problem number one, we have x to the fourth minus 81. We have an even exponent right here, so this would be a perfect square. And then we have an 81, which is also a perfect square, and we are subtracting the two of them. Excuse me. We're subtracting a perfect square from a perfect square. So the square root of x to the fourth, the square root of x to the fourth is just x squared. You just divide the exponent in half. And then the square root of 81 is 9. So we're going to split this up. We're using this x squared and this 9. X squared plus 9 times x squared minus 9. Notice we have different signs right here. Well, looking at the second part of this problem right now, we have another perfect square. We have an even exponent, and we have another perfect square in 9. So the square root of x squared is x, and the square root of 9 is 3, and they are separated by a subtraction sign. We cannot do this over here because it's addition, has to be subtraction in between. So let's split it up. I'm going to write the first part of this, x squared plus 9, times x plus 3 and x minus 3. So we had a plus and a minus, a plus and a minus, and then we just left the first part here. Moving on to problem number 2, we are going to graph. Sorry, just looking at the numbers over here. We're going to graph this problem. So we are going to go back and find the steps from the 3.1 notes in order to graph on Savas. Just looking at this equation, we have an x-intercept at 0, 2, and negative 2, because 0 makes this term 0, 2 makes this term 0, and negative 2 plus 2 would make this 0. So I know I have intercepts right here. And then also we have a y-intercept at 0. But if we graph it, it'll just tell us that this graph looks like this, and we can find the x-intercepts using that show trace line. We could also find the one y-intercept. I think we gotta bounce around here. Yep, so problem number 3, we have y equals x cubed minus 6x squared minus x plus 6. First thing problem number 3 asks of us is finding the end behavior. So from earlier in chapter 3, we're going to look at the leading coefficient and the degree. I believe that was 3.1, I want to say. So our leading coefficient is 1, that's a positive number. Our degree, our biggest exponent, is 3, that's an odd number. So from the notes, yep, 3, 1. If we have a positive leading coefficient and an odd degree, as the graph goes left, it goes down, and as the graph goes right, it goes up. Next thing it's going to ask for is our x-intercepts. So we are going to factor this down by grouping. So we have 2 underlines right here. I'm just going to look at these first 2 terms. We have x cubed and negative 6x squared. What do they have in common? X squared goes into both of them. So let's pull out an x squared. And what's left over? X squared times x is x cubed, and x squared times negative 6 would be negative 6x squared. So I just pulled an x squared out, and this is what was left over. And then when we group on the right side, we want both things in parentheses to be the same. So I have negative x plus 6 right here, but I want it to be an x minus 6. So I want to switch the sign on the negative x and switch the sign on the plus 6. How do I switch a sign? I pull out a negative 1. So now we have x squared times x minus 6 minus 1 times x minus 6. And now we have the same thing in the parentheses. We're going to take both the double underlines right here, and we're going to put them together. So x squared minus 1 times that x minus 6. And now we can just solve both of these quantities, set them equal to 0, and find our x-intercepts. So x squared minus 1 equals 0. Let's add the 1 over to both sides. X squared equals 1. Let's take the square root, and x equals plus or minus 1. So there's 2 x-intercepts right there. And then we have x minus 6, set that equal to 0, add 6, and x equals 6. So right now we have 3 x-intercepts. These are also called roots or zeros. The next step of this problem, we're going to find multiplicities of our x-intercepts or of our roots or zeros. Multiplicity just means like how many times are you going to write it. So we had 1 written 1 time, so I had a multiplicity of 1. Negative 1 was written 1 time, so I had a multiplicity of 1. 6 was only written 1 time, so it has a multiplicity of 1. All of these are odd multiplicities. So on our graph, just like we'll see on our next page, the line is going to cross straight through the x-axis. If any of these were repeated over here and they had a multiplicity of 2, that's an even multiplicity. So the graph would kind of touch the x-axis and then go right back down or right back up. But all of these roots are going to pass through the x-axis. And then we see right here, we're going to find our y-intercept. So all you have to do is plug in 0 for all the x's in our equation, or it's just the constant right at the end, right? So we plugged in a 0, 0, 0, and then 6 was what was left over at the end. So this graph is going to pass through at y equals 6. So here's our negative 1, here's our 1, here's our 6. Those are all of our x-intercepts. And then our y-intercept was up here at 6. And notice going back to the multiplicities, they were all multiplicities of 1, so the line just goes straight through the x-axis, straight through. It never would like touch and go back down. It always just goes right through. And then just looking at this graph, so you can zoom out on your graph on Savas, is this symmetrical? No, it's a funny shape, right? It doesn't look even. Is there a line of symmetry? Well, since it's not symmetrical, you can't cut this graph in half. So there's not a line of symmetry. Moving on to problem number 4, we want to find the zeros of x cubed plus 6x squared plus 9x. In order to find the zeros, we're just going to find the x-intercepts. I forgot a 9x here at the end, but it doesn't fix the later steps in our problem. So we're going to pull out an x from all 3 of these terms. Remember, there's an imaginary x. I'm going to pull out an x, and now we have x times x squared plus 6x plus 9. And then we can factor this with x plus 3 and x plus 3. 3 times 3 is 9, 3 plus 3 is 6. And then we're just going to set all 3 of these terms or quantities equal to 0. So x equals 0, x equals negative 3, x equals negative 3. Notice here these 2 roots or zeros or x-intercepts showed up twice. So our roots are 0 and then negative 3 with a multiplicity of 2. Then we want to find out the behavior at these zeros. So when x equals 0, it only showed up once, so it's a multiplicity of 1. That means it crosses through the x-axis. At negative 3, it showed up twice, so there's a multiplicity of 2, so it's going to touch the x-axis and go right back to where it started from. In the last example, we were doing the same thing. We're going to factor it. There's 4 terms, and they don't have anything in common, really, so we're going to group. So we're just going to look at these 2 and then these 2. What do x cubed and negative 3x squared have in common? They both have an x squared, so let's pull out an x squared. What would be left over? If we took an x squared out of x cubed, x is left over. If we took an x squared out of negative 3x squared, a negative 3 is left over. And on the right side, we want our parentheses to be the same as this x minus 3. So we want this x to be positive, and right here we have a negative 64x. So let's pull out a negative 64 in front, because now we just have a positive x left over. And then negative 64 times negative 3 is positive 192, so it checks out. We're going to group these together, so x squared minus 64, and then x minus 3. Notice this is just like the first example. We have a perfect square, x squared, and we have a perfect square 64 of 8, and there's a subtraction in the middle. So this is going to split up into x plus 8 and x minus 8. Opposite signs right here, and these are just the square roots of 64 and the square roots of x. So what are our zeros? Pretty much what number would you plug in for x to make this 0? Negative 8. What number would you plug in right here? Positive 8. What number would you plug in here? Positive 3. There's our x-intercepts, our zeros, our roots, whatever you want to call them. They all have a multiplicity of 1, so they're all just going to go straight through the x-axis. 3.5 and 3.6 can be difficult. So if I think personally, I would watch one of these examples, go to the homework and try that problem. And then if you don't get it on Savas, go back and watch the example again. Try it again. If you don't get it then, maybe question help button or send me an email. I'm happy to Zoom.